Well, it looks like it's just about that time. Welcome back, everyone. We've got a lot of announcements here, so let's just run through them. But before I start talking, any questions you want to ask or address right away? Okay, well, let's just go down the line. Currently, we're in section 5.1, and we really have only 2 instructional days left. And that's kind of exciting in a way, right? It means we're almost done. We're going to work on section 5.1 today, look into section 5.2 when we come back on Monday's class. That means that's just probably more likely or not than not going to be the last section of the whole course. Kind of nice. Next thing I want to discuss is that there are a lot of extra credit opportunities available to us now. And let me go in reverse order. The first extra credit opportunity is relative to quizzes. If there's a quiz that you didn't get in, it went late, maybe life got busy, anything along those lines, I have been accepting those quizzes for full credit. So take a look at the grades up in Moodle, see on the quizzes if anything's missing. I'll be happy to accept them. Another way to get extra credit is the due dates in WebAssign. They're all about pacing. So if something went past due, get back into the system and you can always request an extension. At any time, you can request an extension as many times as you like. It doesn't annoy me in any way, shape, or form. And you don't need an explanation of why you're requesting an extension. You can just directly ask one, leave the comment field there blank. But the thing to keep watch out for with both the quizzes and in WebAssign is Monday is going to be considered the final day of the course for submitting materials. So that'll be the last day to send in quizzes, last day to work into WebAssign. After that day, those scores will become finalized. And on that same day, well, we have two courses running as one. So this is always a little bit confusing. There's the in-person section, which has 2 people in person currently. And for us, the final exam is Monday, April 29th. And it will be from, this is always the worst part, the registrar does this. I don't get to choose these times. 8 p.m. to 10 p.m. It'll be in this classroom. So that's a late night. I do write an exam with that in mind, that that's not an ideal time to take an exam. And I also, when I grade final exams, that's the one exam I sometimes do curve. I'm not going to try to write a final exam that cuts everyone's grade down. If you take a look at where your grade is right now, then this is what I actually really do on a final exam. After I grade it, I look at the average grade in the course. If it went down, say 3%, I curve the final exam and I bring the average grade of the course back up to about where it started. I can only curve within so much reason, but if everyone's grades on average went down by 5%, then I do curve that final exam. It's not meant to be an exam that cuts people down. It's just more of a formality. We're required to give one. So for students that are in the in-person section, the final exam will be Monday, April 15th at that time. Then the other course, section 11, I'll be sending your exam to the Pocatello Testing Center, and I'm going to try to do that soon so that there's less issues about scheduling. And once I get that done, I'll be directly emailing you to let you know you can contact them to schedule your exam. So you're not required to come in person on this campus. It's assuming that you may not even be near the Pocatello campus if you're on the fully online section. But any questions, folks, with any one of those announcements so far? Okay, I think we're really right here. I got sidetracked on the final exam. The big extra credit opportunity is really this one. I got the style of doing this because oftentimes people want extra credit at the end of the semester, but I found that when I gave like actual extra credit you might expect, something that's extra extraneous to the course, that is usually a disservice in a certain sense. If I gave an extra credit that was just go beyond, get a really good grade on the final exam, learn the course material really well, that's the one that's usually the most meaningful. And so this is really my bigger extra credit opportunity. If you had a rough exam among exams 1, 2, and 3, let's say, for example, just exam 2 was an off day for you. Maybe you were sick, but you came in, did the exam anyways, that kind of stuff. Or maybe just work got busy. You weren't as up on that material. So if exam 2 was really bad for you, but you kept on with the course, you studied the material and came back, and your final exam score is larger than your exam 2 score, it will fully replace it at the end of the semester. This extra credit opportunity can't hurt your score. It could only improve it. Any questions about this opportunity here, folks? Okay, so the next one is more because it's really hard for some reason to get, for the math department to get course evaluations. We used to do them on paper, but for the last 4 years, we've been doing them on Moodle. I guess we just don't have a great strategy for getting a lot of evaluations. So to help them out, I started to do this extra credit opportunity. The course evaluations are going to close on April 26th. That's going to be Friday of next week, so right before finals week, essentially. If you complete the course evaluation and take a screenshot of the completion page, it just says, thank you for completing the course evaluation, email it to my ISU email address, and I'll drop the lowest 2 homework assignments and WebAssign at the very end of the semester. So that may not be a huge deal in terms of extra credit, but WebAssign's kind of a jerk sometimes. And it's almost like a fairness thing, I'd say, to drop those lowest 2. To get that extra credit, you have to email me that completion page at some time, but the actual course evaluation does close right on Friday, the 26th. Any questions so far about that one, folks? Okay, and as far as actually finding the course evaluation, it's right over here. You have to click on the arrow that says open block drawer. Some people might already have this open all the time. And I moved it to the very top. The course evaluation is right here. You click on it, you get this big wordy explanation of why it's important. I don't know if that's the best approach by the math department on getting people to do course evaluations, throwing a wall of text at them. But this is the math department really wanting those evaluations because the State Board of Education told them so. We're a state college, so if the State Board of Education says jump, we clarify by asking how high. So you're not required to do these. Just keep that in mind. It's all totally up to you. If you do decide to answer those, click on this button, and I believe that takes about 15 minutes. I think that's a high average. Most people probably are going to get these done maybe more like 5 or 7 minutes. When you answer all those questions, take a screenshot of that completion page, directly email my ISU email down here, and I'll reply back, thank you, something along those lines to know you got your extra credit. Any questions about that at the moment? Okay, and if you are just way on top of things and you notice something new occurred here on Monday and you want to do this, you already have done this, that's okay too. Just click on it again. Click on this button and it'll say you've already completed this evaluation. Take a screenshot of that and that's just as good enough for me. So either it'll say thank you for the evaluation or you've already completed it. Those will both get you extra credit. So either take a screenshot, cell phone picture, anything like that will work out for me. That is like almost 10 minutes of talking so far. But any questions, folks, at the moment with any of those announcements? Okay, so when we come back next week, we will be reviewing for the final exam a week away from today on the 24th, but we won't be doing those problems. I left that here. That's pretty much primarily just for you. So that's a huge document on problems on a section by section basis. Some of those sections go beyond where we're going, section 5.2. So just stop right around here. Our final exam is comprehensive, but only on the sections that we completed. When we actually do our review, you'll see more documents down here. I'm going to post things like old final exams, and that's the kind of review that we're going to take a look at. An old final exam to get us a feel for what will a 2-hour exam look like after doing 75-minute exams. Well, that's all of the announcements, I think, unless I forgot something. I'll email you all if I did. For the moment, we're going back to section 5.1. Let me bring back the participants window. But any last questions, comments, or concerns about the final exam, those extra credit opportunities or otherwise? Okay, well, let's begin then. In section 5.1, we're turning over from the process of differentiation, which we spent most of the course on, into integration. Like we mentioned before, this section bridges the gap, antiderivatives, but that doesn't become very clear until you get a little bit further into chapter 5. First thing we have to do is look into how do we compute or estimate areas. So this lays out the problem before us. It's called the area problem. And it's contrasted against the tangent line equation problem. That one was all about derivatives. The area problem is all about integration. So what we want to find is the area under this curve, y equals f of x. We want this curve to be nice, continuous from the closed interval from a to b, because if it is nice and continuous, this looks like a very, very solvable problem. Except that curvature that you see here is making everything difficult. If that blue curve looked like this instead, that's not too big of a problem. You would just divide this up, find the area of the rectangle below, the area of the triangle above, and your work is done. Not going to be so friendly on these kinds of functions here. They have curvature to it. So we need a new strategy. What we'll do is partition the real number line from A to B. We call A x naught. Then we decide on a distance. This is going to be a uniform distance to get to the next cut point, and the formula is always going to look like this. If the variable is x, we'll go delta x equals b minus a divided by n, where n is going to be equal to the number of approximating rectangles. So n is the number of rectangles. This delta x, this is equal to the width. Let me see if I can spell width a little bit better. Let me do it this way. Delta x equals the width of the rectangles. So once we decide how much precision we want, a large value of n is going to give us a really great approximation. Small value of n is going to give us a blunt one. But in either case, delta x is going to be the width of the intervals. And so this is what it looks like. We go from a to a new value x1. And this x1 is going to be found by taking that delta x and just adding it in. So in other words, x1 is a plus delta x. Keep on adding in those distances. So here's x2, x3. Geez, pretend those are exactly equal widths. That wasn't well devised, but we'll go with it. And this one will be xn, whatever n happened to be, 4 in this case. So once we decide on the width, the intervals, here's what the rest of it looks like. We need some point. Maybe it's the far left endpoint, a midpoint, a right endpoint, or just any point inside here to decide what should the height of the rectangle be. Let's take right endpoints because that's the first one we're going to take a look at. We take right endpoints, we draw a line that goes up, hits the curve, and it's got to be a rectangle, so it flattens like this. At x2, we do the same thing. Draw a line that comes up, hits the curve, however the height that curve got, comes over and comes down, and then just rinse and repeat. On the last one, B, this rectangle only goes to here, and this is what our area of approximation would be. It's not hard to calculate the area of each one of these rectangles. In fact, we can put down the formula right here. The area of that one rectangle is going to be equal to, well, you'd have to take delta x, that's the width of the rectangle. Then you have to multiply it by this height. What is that height? Well, it's specified by the curve y equals f of x. So whatever that height is, that's going to be f at x1. So that's how we'll get the area of this segment. But notice it's approximating rectangle definitely. It's an under approximation right here. All of this area is unaccounted for, and the only way to make the approximation more precise, make more rectangles in there. So every one of those rectangles is calculated in this area. Second rectangle is an overestimate. So is the third one. And the fourth rectangle is a massive underestimate. We left out all that area right there. So that's going to be the name of the game. If we can make these approximations work for us, we're actually developing the tools for integration, finding the right areas under the curves. So this picture is not anything we can calculate, but the big takeaways are, this is a big formula we're going to be using a lot. And we're going to be using these kinds of expressions to build out the areas. So if we wanted all the area, we would say just delta x times f of x1 plus delta x again, multiplying f of x2. And this gets tedious, but let's keep on going, plus delta x times f of x3 plus delta x. Oh, and that's supposed to be color-coded. Let me fix that. Let me come up with a faster way of switching the pen color, but if I'm a little bit slower here, at least you have time to catch up writing it down too. I want to call it x4, but we called it xn, so I'll keep that same description. So this will be the approximating area. And by what we see here on the diagram, there's a lot of area here and here unaccounted for. The overestimates are minimal. We would say that this is this is a under estimate. Because the areas that we're calculating are missing a great deal of quantity. Well, any last questions, folks, with this initial example here? Okay, so that seems like a natural approach. This is how we get areas under the curves. But I think the most important question we might want to ask and answer is, why do we care? Why are areas important? We kind of hinted at it a little bit, but I think this is the most important problem in section 5.1. This one right here is a great description of why areas out of nowhere seem like they're a big deal in a calculus class. It's because of these kinds of problems. Let's take a look at just what's happening on this graph. The velocity graph of a car accelerating from rest to a speed of 120 kilometers per hour over a period of 30 seconds is shown. So this is just saying, where is their speedometer at any moment of time, essentially? It looks like you're probably in the European Union or something with those units. So we've got a velocity, we've got a time, and this is just the velocity curve, the derivative v. What we want to do is estimate the distance traveled by using 6 approximating rectangles at right endpoints. This means we're using n equals 6 for the 6 approximating rectangles. When it says at right endpoints, that also means we're using, for the right endpoints, we say r, and 6 to say 6 of them all together. So that's our shorthand for the right endpoints. We'll round our final answer to 4 decimal places and also decide if we're over or underestimating the distance traveled. So that's what we want, and it seems kind of vague in a way, right? You have a velocity graph. You can't directly say what the distance is just by reading the graph. You need something else. And if you're thinking back in algebra, the formulas that you might think of are distance equals rate times time. So we could use that formula there, but we've got a problem. The problem is the rate of speed is the velocity given here, and velocity varies. That's unfortunate. The curve looked just like this. That wouldn't be so bad to get that area. We would just say that the distance is the rate, let's say 120 kilometers per hour times time over 30 seconds, and that would make sense here. But velocity varies as it does. We need to be very careful. Getting the area under a curvature like this is not so easy. And so that's why we're approximating with rectangles. And that formula tells us that's a sensible thing to actually do if you want a distance out of this. So let's start actually making this process happen for us. And any kind of problem, whether it's an applied one like this or otherwise, there's a definite sequence of steps you'd want to take. This is your typical step 1. Calculate delta x right away. Let me make sure I keep the same color coding. Let's keep green for delta x. Delta x by formula is always b minus a divided by n. But we have to know the meaning of these things. B is always going to be taken to be the upper endpoint. So that 30 there is B. We'll also call it T6 because of this right here. And I'm reminding myself of a problem here. This is time. That should be a delta T. Let me fix that right there. delta t, only because we have t down here. If that was a z, we would have called it delta z. I usually think of these in terms of x. That's why I love x, I guess, for delta x. But this is a better description of this problem. So the b is the right endpoint. The a is the far left endpoint, which is 0. And so this goes 30 minus 0. The n is the number of approximating rectangles, which are 6. So 36 would be 5 seconds. So that's our delta t in this problem. There is a other issue going on with this problem. Notice that the velocity is in kilometers per hour, whereas the time is in seconds, which is natural, but that's a unit mismatch. We're going to have to correct that in this problem. I typically don't do that on exam questions. It's just kind of an annoyance, honestly, but it's part of real life, so we'll do it here for the homework problems. So after step 1, I would say this is the next most important step to take, our step 2 here. We want to definitely indicate all of the values in the partition of this t-axis we're going to list out. So we'll write out t naught. Typically I'd put x naught. I think I was just about to until I corrected myself. T naught is just the far left endpoint, so this will be 0. Now we go to T1, and all we're doing to get all of the endpoints is we're adding delta t to each outcome. So if delta t is 5 seconds, then the next outcome or interval is going to be 5, and then just keep on adding delta t. T2 is 10, T3 is 15. The good news is there is a built-in check here. We're going to end at T6 because there are 6 intervals, and we should also hit 30 seconds because that's the end of the interval. So let's double check we get there. T4 is going to be 20 seconds. T5 is 25 seconds. And let me see if I can scroll just a touch. There we go. And then the last one, T6, would be 30 seconds. So just add delta t repeatedly. If you've got 30 seconds, when you hit T6, then you're on the right track. So these are all of the endpoints. But the next thing you have to decide is, which rule are we using? It could be the left endpoint rule or the right endpoint rule. If it's at right endpoints, then you would use these. These are the right endpoints. If it said left endpoints, we would have grabbed these instead. We'd use the far left endpoint and go all the way to the penultimate one, 25. I will see that in the very next example. But right endpoints means you skip the leftmost endpoint, and you're going to end at the rightmost endpoint, T6 for 30 seconds. I think that's a confusing element of these kind of problems as well. So examples 1, 2, and 3 are just meant to show what you would do at right endpoints, left endpoints, and then midpoints. We can also just kind of circle this in that same color to convey, if it's R6, here's where you're going to get your right endpoints. So that's step 2 down. Now, the next thing I'd want to do is, if you have a graph here, it's not a bad idea to fill it in because we can determine if we're on the right track and also use the graph to determine if the estimate is an overestimate or an underestimate. Let's plot down all of these endpoints. Right over here at A, this one's going to be T naught, but we're more interested in T1. Here's T1 at 5 seconds. This one is T2 at 10 seconds. T3 is here at 15 seconds. Let me actually put these in. 20 is T4. Here is T5 at 25 seconds. And the 30 seconds, so that we call B, is going to be our T6. That doesn't quite work. Let me use the arrow strategy. So there's our T6, the 30 seconds. So once we have done that, if we're at right endpoints, then this is what the shading is going to look like. Go to T1 at 5 seconds. So right here, draw a vertical line until you hit the graph. We're stopping right at this location. Go all the way to the left, and that's our very first approximating rectangle. Let's see if we can correct the vertical scale as well. They didn't print a lot of information. So this will be 20, 60, 80, 100. They told us it ends at 120, but it's just comforting to actually see that. So let's throw that in there as well. So here's our first approximating rectangle. Already looks like we're getting an overestimate in this case. So that's probably the right situation. Now we go to T2 at 10 seconds. We're just going down the line. We put a vertical line, hit the graph and go left. And that's our next approximating rectangle. Now recall distance is rate times time. And if you take the height, that's the rate, about, looks like, say, 50 kilometers per hour. The time is the delta t, 5 seconds. So it's an overestimate, but it's at least a pretty good estimate instead of just kind of guessing based on the curve. So let's fill in the rest. At T3, this will be the next height. T4 for 20 seconds. There starts to be less change in the velocity. And notice how there's less change in the velocity means the overestimates are decreasing as well. At the initial portion, the velocity changed a lot. It was starting to accelerate. And that means we overestimated by a lot as well in that rectangle. If the derivative gets close to 0, though, our approximating rectangles start to do a better and better job because a derivative of 0 is going to give us a horizontal curve. Those are much easier to estimate areas on. So here's the last couple at T5. And the last one at T30. And our goal is now to find the area of all those rectangles. So we're ready now for step 3, or we just write down the formula. Any questions first, folks, to this stage? Okay, well, our formula is basically this right up here that we did. But that's a clunky formula to work on. One thing we typically do is factor out the delta x. I like it in this format if you're thinking of the concept that this one piece got us the area of that one rectangle, but in practice, that's a lot of copying. It's unnecessary. So when I go to indicate the formula, I usually go like this. The distance is going to be approximately equal to this quantity we're calculating, R6. And here's the formula. R6 will be delta t multiplying the group. I'd usually say f of something, but that's a specific function. Let's use v for the velocity function. It'll be v at, if it's right endpoints, t1 through t5. So v at 5 seconds plus velocity at 10 seconds, velocity at 15 seconds, velocity at 20 seconds, velocity at 25 seconds, and I can never seem to get that at one line. Let's drop a line. If this ever happened to you, then this is totally legitimate. Just drop a line and keep on adding, plus velocity at 30 seconds, and then close the bracket. So that's the formula that we're going to involve. We have to visually estimate all of these values, but if you ever have to do that on an exam, don't worry about it. I'm pretty forgiving on these. If you're off by a little bit, I don't worry. If you said this value was say 10, then that's the only time we'd have a problem. To me, that looks like about 50. So let's go with that. This is approximately equal to, first delta t was 5 seconds. We're going to need to correct that. Let's see here. 5 seconds would have to be multiplied by 1 minute per the 60 seconds, which would have to be multiplied by 1 hour per the 60 minutes. Again, kind of annoying work on units, but it's necessary because velocity is in kilometers per hour, not kilometers per second. Then we do these kinds of cancellations. We now have something in terms of hours, and delta t is going to be 5 divided by 60 squared. This is a good time for a calculator, I'd say. So 5 over 60 squared gives us that figure. That's kind of awkward to work with, but It's also 1/720. I think that's a little bit easier to put in this exact value. Let me double check that. I don't quite like the decimal answer. That's clunky as well. But 60 squared is 3,600. 3,600 divided by 5 is 720. A little bit easier as a fraction, 1/720. I'll leave it up to you how you'd like to write it in. So for delta t, we have 1/720, and this is in hours. Okay, now finally we're back on track, getting those velocities. I'm just going to go down the line, reading them off the graph. So up here, this would be about 55 kilometers per hour. And this is how we know we're on a pretty good track. We're really getting distance because this thing multiplies and cancels the hours units, leaving just behind kilometers, which is what we expect for the right measurement. So down the line at 10 seconds, this one looks like about 80 kilometers per hour. Then at 15 seconds, a little bit harder to check. Let's say about 95. And a few more. Let's see, at 20 seconds. Oh, let me double check. That's 1, 2, 3. Yes, we're on 20 seconds next. This one looks to be, let's see, maybe it's 110 kilometers per hour. Now, next at 25 seconds, well, we do know it caps out at 120 kilometers per hour. This one's pretty close, so how about 115? Again, it's all visually estimated, so you might have said 117, 118. I'm totally fine with that. It's in kilometers per hour, so let's put that in as well. And then the last one, this is the only one I have an exact value on because they told us that it accelerated to a speed of 120 kilometers per hour. So there we have amount of time multiplying different rates of speed. So we really are using distance as rate times time, but just in a slightly strange and clever way. Last thing to do is put it all in the calculator. This is the tedious part. Also, it's another reason why calculators are allowed on exams because of all this typing. But if you have to do this on WebAssign, we'll do it here as class as well. So 1/720 to start. Then it's going to multiply 55 plus 80 plus 95 plus 110 plus 115 plus 120. And we get this figure right here, 0.7986 kilometers. Doesn't seem so impressive when we were doing 120 kilometers per hour, but keep in mind this is only over 30 seconds. And for about half of, well, maybe about a third of those 30 seconds, we weren't really going that fast either way. So that's what it settles down at. Any questions at all, folks, on getting through that process there? Okay, definitely kind of weird stuff for sure. But this problem is an attempt to say why areas are important. Any physical quantity that you can conceive, you can reframe it as an area problem. And so, well, makes it seem like finding areas is even more important than differentiation, but they're actually connected as well. That's the amazing fact. That's why this section is important. It turns out that finding areas is all about differentiation, but specifically, you need an antiderivative. So there is a strange connection between derivatives, the antiderivative, and that highlighted area. We'll see more and more of that as we get further into the notes. But let's take a look at another problem next, just to get some more practice. Any questions at all, folks, on running through this one? Okay, here's our next one to take a look at then. This one's not an applied problem. This one's a little bit more similar to just a generic WebAssign kind of problem. It says for us to estimate the area under the graph of f of x equals natural log x. If this was a real exam question, I probably would print the graph for you of that function. If it's a homework problem or a WebAssign problem, you're heavily encouraged to use any kind of software, whether it's a graphing calculator, Desmos, or otherwise, and just plot that out to get a feel for what's going on. It's also important because we want to decide if it's an underestimate or overestimate, which reminds me, we forgot to do that on this problem here. We indicate overestimate, but I don't feel like we really finalized that. So let's put here and say, just to tie that in, this is an overestimate. Okay, didn't want to neglect that part. It's always good to read the instructions multiple times. And now let's come down here and do it all over again. So first thing we want to do is produce the graph. Let's use technology, take it easy on ourselves. Y equals natural log x. If you're using Desmos or a graphing calculator, this is never really good enough. You need to specify the domain. So Desmos go curly bracket, 1 less than or equal to x, less than or equals to 9. And this is what we're working with. Just that right there. That ought to work for us as a screen graph. So let's take that, and there's our problem. That probably doesn't need to be this big. That should do the job. So we're going from x equals 1 to 9. So here's our value of 1, which is sometimes thought of as a, and confusingly also thought of as x naught. That's kind of unfortunate in the terminology. We're going all the way up to 9, so here it is at 9, which is thought of as the b, which can be thought of as, let's see here, there's 4 approximating rectangles. That would be x4 in the problem. So let's go down the order of operations for this, or steps rather. In step 1, we need to know the width of all those approximating rectangles, and that's the delta x. So this is by formula b minus a over n. So our b is our upper limit, 9 minus a, our lower limit of 1. Our value for n, let's see here, it said 4 approximating rectangles, so n is 4. So we're dividing by 4, meaning this is 8/4, so exactly 2. It's kind of nice, even number for us to work with. We're using left endpoints, so we need to approximate at left endpoints. And let's say now for step 2, let's write down those points and see what they're going to look like. First one is x naught. That's the value of 1 right here. Then for x1, again, all you're going to do is take your width 2 and just add it to all of these. So the next one should be 3. Let's put a paper trail in the notes though. Add delta x. So we are only going to go for 4 of them on this one. That's kind of nice. On a real exam, that's probably what I would do. I don't want to give a huge amount of tedious, busy work on a real exam. So those are usually going to be pretty low counts, 3 or 4, something like that. So x2 will be 5. x3 will be 7. We're going to end at x4 and double check. I have to add 2 to get 9, and it had better be 9. So that's a good internal check on the process. Next thing that's kind of confusing is if you're using left endpoints, that means that would be these right here. We do not use the far right endpoint if we're using a left endpoint rule. These are the so-called left endpoints. So those are the actual function values that we're going to be using, the inputs to the functions. Last thing to do in step 3 is just to write out the formula and calculate it all out. So it is a methodical process, but this is a kind of a different way of doing math in this class, I'd say. So I'd say go slow at first. It definitely feels unfamiliar when you're starting out this one. And I would say to me, the most confusing thing about this, or at least the most questions I get about it, is how do you determine the endpoints? Well, watch out for this instruction. If it says right endpoints, then you're excluding the left one. If it says use left endpoints, then you do use the left one, but you're excluding the far right endpoint in that case. So that's the setup so far. Now, just so we can answer this last question, is it an under or overestimate? We're also going to plot these rectangles. And I mean, that's a good idea too, because seeing is believing, we'll be able to determine if this even looks right when we get an area. So I'll use this pen here, or pencil, for the areas. The first one is at x naught, which is 1. And that means you go right here. You only go as high as you have to go to hit the curve, but it did hit the curve right at this location. This rectangle is like a pathological one. It has height 0. And that's just because the function itself had height 0. We get no area there, and so already massive underestimate. Then we go to the next one. It's at 3, so let's put that in. Oh, you know what? We should probably put these all in to start. It goes 3, 5, 7. That should have been really a very important first step. So here is x naught. This is x1, x2, x3 where we're ending. And because I put down that point, it's now more clear that this rectangle extended all the way to over here. It would have been a mistake if I didn't put in these actual values in clearly. Now the next one at 3, we go right on the x-axis, go up until you hit the curve, and we have to move right this time because we started at a left endpoint. And I didn't go far enough again. It just seems like a really wide value. Then on the next one at 5, go up, hit the curve, and just rinse and repeat. Here's the last one. This one goes all the way to the right at 9. At 9, this comes all the way up. And so here's the shading for those rectangles. Already, this looks like an underestimate. It's underestimate by a pretty decent amount in every one of these regions, especially right here. That's missing area by the red dot. So in case I forget, I'm going to put down here, this is an underestimate. Okay, no danger now. We're not going to forget that one element of the question. I'd say it's a decent test-taking strategy as well. I try not to put a bunch of questions in one statement. I like parts A, B, C. But sometimes there is more than one thing you have to check, and if you are worried about forgetting something, just put it down right away. For step 3, here's what we're going to do. We want this area in blue, so we'll say that the area is equal to approximately, it said left endpoints. And so if it's left endpoints, that means we're going to use L4. L to say left, the 4 because it's 4 approximating rectangles. So down below, area is approximately equal to L4. Here's the formula for L4. You take delta x, then you multiply it by f of x naught. You just use all these left endpoints, so it'll be f of 1, f of 3, f of 5, f of 7. If you've got 4 values in there, then you're matching the n equals 4 and just stop right here. It's not an uncommon mistake to go to the next one, f of 9, but that's not part of the left endpoint rule. We're ending right here. So next thing we do is just plug in information. This is going to be equal to, for delta x, we have a value of 2. Then it's going to multiply. Well, it says f of 1, but now you need to look up that function. It's way up here. F of x equals natural log x. We could have conveyed it here. Y equals f of x equals natural log x. And so the values drop in like this. Natural log 1. Now double check, just be for the fun of it. Natural log 1 is 0. So we're getting a 0 quantity here, but that matches up with the graph. It had height 0, so we should be getting area of 0 from that contribution. So it's nice to see that everything is at least consistent with what we're seeing and what we're doing analytically. So next one is going to be plus natural log 3, natural log 5, natural log 7. All because the f function was the natural logarithm of x. So that's what we're calculating down here. And that means we're ready to get the end answer. Any questions, folks, before we jam all that into a calculator? Okay, let's make this happen. Grab your favorite calculator, whichever it might be. And I'm going to write this out the way I would do it as if we were in an exam setting. Usually you don't have any great tricks in your calculator. You're just plugging it all in at once. So it would look about like this. 2 times. If you typed in natural log 1, no harm done, but didn't do anything for us. So the more you skip, the faster you are on these. Plus natural log 3, plus natural log 5, plus natural log 7. And there's our value. We're getting an area of about 0.9307. Let's follow those instructions, 0.93079. I said that weird, that's 9.3079. There we go. Well, any questions, folks, on getting that value so far? Okay, well then checking on the graph, yeah, that definitely looks like an overestimate for sure. Excuse me, underestimate for sure, looking at those areas. But you can do another thing to just to determine, is the answer of 9.3 even reasonable? Here's my check on this, and it's not a great check, but it could serve you well in an exam setting. If you thought of the problem like this, then you know what? I can calculate the area of that rectangle pretty fast. Rectangles are great. Let's do it right here. It would be a height of 2 times a width of, from 1 to 9, that's a width of 8. So if I did the red area, that's an area of 16. Now, this doesn't work, but it still gets you closer. Imagine you cut that area in half. That means you're just looking for this. It's not quite right, but it gets us a little bit closer. So go back in Desmos or your calculator, divide it by 2, and it tells us we should be in the neighborhood of about 8. If your answer was 93.079, we're way off. If it was 0.009, also way off. This is a horribly crude way to estimate, but it gets you in the right neighborhood of the answer. So making a 9.3, comparing it to an area of 8 with a bad estimate, says that's good numerical evidence. We are on the right track with that answer there. Any questions, folks, with the conclusion here? Okay, it looks like we did it, but let's take a look at another interesting problem just to make a connection. In section 4.6 with antiderivatives, we tested out this thing, that x natural log x minus x is an antiderivative of natural log x. And you know what? That's exactly the curve we're taking a look at. Let me see if I could just minimize that a little bit. Okay, so right here is what I wanted. This function, we tested it out. When we differentiated, we got natural log x back, the same function here. So x natural log x minus x is an honest antiderivative. Now, here's the bold claim. This is the fundamental theorem of calculus. This is a culmination of a lot of work from Isaac Newton, Leibniz, in different places in Europe. They found that if you took, if I get a calculator first, if you take that antiderivative, x natural log x minus x, and plug in the value of 9 first. Let's do that. I'm putting a 9 in, so 9, natural log 9 minus 9, then go minus and do it again, but with a lower limit. I'm going to plug 1 inside here. So 1, natural log 1 minus 1, then you should be getting the exact area. It looks off though, right? Because our area came out as a 9.3079, but that was an underestimate. That's the exact area to this level of digits. And that's kind of a remarkable fact. All you need is the antiderivative to this thing, evaluate it at the upper limit minus the lower limit, and there it is. That's the true and exact area. It's almost a freaky fact in a way, but it seems believable in a certain sense. When you think of, that's all we're doing right here. Distance is rate times time, and the distance function is an antiderivative of the velocity function. differentiate your distance function and you get velocity. So already that seems plausible, but it's still kind of a weird fact when you're looking at it right on paper like this. Well, I think that's all we have to say about this one. Any questions at all, folks, on this problem here? Okay, let's change gears and take a look at the next one. So, it needs to delete stuff. Let's hope Control Z brings it back. Okay. So the next thing to take a look at is midpoint rules. You might have noticed that when you use the left endpoint rule, that didn't seem like the smart way to estimate on this problem. And when we use the right endpoint rule, that didn't seem like the smart way to estimate either. If we compromise between right endpoint and left endpoint, taking a midpoint, then we're balancing the over and under estimates on a lot of these kinds of problems. So that's why the midpoint rule takes on a special quality. And it's a great way to estimate. It just involves a little bit more computation. So I think we have enough time to take this on. Let's give it a try. First, here's the function we're going to work with. We're going to estimate that from -2 to +1 with 4 approximating rectangles. Let's just start summarizing the process right here as we see it. From that statement, n is 4. These are going to be at midpoints, so that means we're going to use M4. So M for midpoints, 4 for the 4 approximating rectangles. Next thing we would want is a way to organize the information. So let's graph this out. F of x equals 1 over 1 plus x squared. We need to put in the right domain. We're going from -2 to +1. So there it is. That's our nice little curve, purple this time. Let's see if we can make that a little bit bigger. Okay, that ought to do the job. So there's our curve. Let's see if we can make it slightly smaller. Well, that'll be just fine, I suppose. So again, on a real exam, I would print this out for you, but it's a good to use this process of using either Desmos or graphing calculator for the homework, because I think these are really, really confusing questions if we don't have a picture to organize and think about the problem. So with that graph there, the next thing we'll do is, for step 1, the most fundamental step is to calculate delta x. Delta x, like before, is taking the upper limit of integration, which is 1, either found on the graph or from the very start of the problem up here. Subtract the lower limit over here at -2. Divide by the number of approximating rectangles, that was 4, and that's our delta x formula. Right? Let me write it down as an actual formula though. Delta x is b minus a over n. We wrote down a couple times, but we're learning this. We should write it down every time. So this is going to calculate to 3/4. That's not so convenient, and this is going to happen in some of the homework problems. If you get a fraction like this, you do have a couple choices. I think for this particular fraction, it's easier to work with it in decimal form, 0.75, so that you're not getting bogged down with least common denominators and all that kind of not necessarily fun stuff in a larger problem. So if you get an exact fraction by dividing, decimal form is probably the easiest way to go. If it was 1/7, it's best to use as a 1/7 because we'd have to approximate this to a high level of decimal values. That's really tedious to write down. The fractions are easier in that case. Once we have delta x, here's our step 2. We need all the boundary points to start, and they go like this. x0, that's always the far left end point, -2. For x1, we're adding a positive 0.75 to each one of these quantities, so it's going to be -1.25, kind of inconvenient, but sometimes the numbers are just not friendly. It's part of life, I guess. Let's put here just for the notes. You're adding delta x, just like on the last problems. Now x2, keep on adding delta x. So -1.25 plus 0.75 is a -0.5. x3 for the next one is going to be 0.25. And x4, this is the check. Add 0.75 to that till we get a positive one, then double check. We did it, we did hit that positive one. So that tells us we're on the right track. But this is a midpoint rule. We do need all these boundary points, so let's plot them in. -2 is x naught. And let's see, -1.25 is x1, and that's going to be about here. X2 is at -0.5, so that one did hit the grid just nicely. X3 did not, it's at 0.25, so that should be about here. And X4 is a 1, way out here. Now, confusingly, these are not the actual points we're going to be using because we're using midpoints. So here's our step 3. We're producing the midpoints, and because they're midpoints, you're averaging stuff, they're denoted this way, X bar, to say you're taking an average. There's several ways to do this, so I'll leave it up to you how you decide to calculate. First, I'll grab the calculator, there it is. Oh geez, and minimize it at the same time. So here's one thought. It's just a midpoint, so you can just take these two values and average them. There's no harm done in that. I think that's a great way to go. -2 minus 1.25 divided by 2 tells us our first midpoint, not very convenient number, is a -1.625. So that absolutely works as a process. I think it makes sense, right? If it's a midpoint rule, you're just adding the two midpoints. But here's another thought. You could take the far left endpoint, -2, add to it delta x. But if you did that, you're getting all the way to x1. You want to go midway. So just divide it by 2, and that produces the first midpoint. So that's decent as a formula goes, but it's really up to you to decide how you want to come up with your very first midpoint. Either average the two, or let's put down this formula, that x bar 1 is equal to x naught plus delta x over 2. Put a bracket around it to say that's an extraneous formula you could use if you choose to. But one thing I would emphasize, you won't lose credit, but this is a good idea. I wouldn't average these two. It's just not an efficient way to calculate. Let's do it anyways. -1.25 minus 0.5 divided by 2. That's our next midpoint, but this is working way harder than you need to. I would strongly encourage you to do this. Go to this value, -1.625, add. Well, you're over here, that's the first midpoint. To get to the next one, just add your delta x. And you get the right value each and every time. This is way faster. So x bar 2 equals -0.875. And it's the same trick as before. All we're doing is adding delta x. So you've got options on getting the first one, do whatever seems natural. But if you add delta x to get all the others, that's a fantastically fast way to calculate. In fact, in your calculator, for just adding delta x again, up here in practice, you're just going to go times 2. That's adding delta x twice. So your next midpoint is at -0.125. Let's do it again. There's just one last midpoint for x bar 4. Convert this to 3, and you've added delta x again, 0.625. So x bar 4 equals 0.625. And again, just to emphasize, if you added those last two, you should be getting this value. That's the check for this problem. It's not the greatest check, but let's see if it works out. 0.25 plus 1 divided by 2. Yeah, we hit 0.625 either way, so we are on the right track. Now, putting these on the graph are actually kind of tricky, so let's take our time with this stage. -0.1625 is going to be about here. Oh, it should be about here, midway. So here is X bar 1. When we go to write the rectangle, you go up till you hit the curve. But now from here, we've got to go left and then right. But notice the nice thing about a midpoint, where the red dot is, that's an overestimate. But then come around over here, it's an underestimate. The over and underestimates kind of balance each other. They don't necessarily cancel out, unfortunately, but it's not as extreme as the last problems. There's a compromise between the two of them. Now for the next X bar, it's negative 0.875, but visually it's got to be between X1 and X2 because it's a midpoint, somewhere right around here. Yeah, that looks about right. Here is X bar 2. Go vertically upward to hit the graph, and then move left until you get to the last value for the rectangle, and then go right until you get to X2. So here's our first one. Here's our second one. And again, there's a compromise. That's the overestimate. This is the underestimate. So let's put down the rest. Negative 1.25 would be about here. And it does look midway between X2, X3. So here's X bar 3. Vertically upward is where we hit the graph. And here's our next rectangle. Finally, 0.625, which is just about here, midway between X3, X4, I'd probably place it about here, is X bar 4. We get a point up here. And this is our last approximating rectangle. I seem to be doing it sloppy because it's the last one. Who knows? We try again on that. So if we can get the area of all those rectangles, our job is done. We would have approximated the area to the purple curve, which is the f of x function, using those rectangles. Well, it's definitely more tedious if you're using a midpoint rule because you use these boundary points, then find the midpoints. But after that, everything is pretty similar. We're going to say that the area, it's approximately equal to what we said we'll use on the start, M4. And by formula, M4 would look like this. Take delta x, multiply against f at x bar 1, f at x bar 2, f at x bar 3, kind of tedious to write all these in, f at x bar 4, and that's our formula. One thing I forgot was to put in the actual values for x bar, and our function f of x up here at the top, I think I'll need to do a screenshot. We'll also have to put that in as well. So we're nearly there, folks. We just need to finalize this statement. Let's say for our next step, in place of this delta x, we'll look it up, and we had a value of 0.75 above. Now for f of x bar 1, here's where it gets extra tedious. So let's see. The f of x function is this, 1 over 1 plus x squared. So 1 over 1 plus, the quantity being squared is x bar 1, which is this, negative 1.625 squared, and that's our very first term. Tedious to write them all out, but let's keep on going, plus 1 over 1 plus x bar 2 is this one, negative 0.875. You can save some time because we're squaring these. The negative sign doesn't actually matter, but that's dangerous because it would have mattered if the power was 3. So I'm putting them in just to be careful. Plus 1 over 1 plus negative 0.125 squared. Here's the last one, 0.625. So 1 over 1 plus 0.625 to the power of 2. We've got it, folks. That's a lot of stuff. Now we have to throw it into the calculator. Doesn't sound fun, but let's get through it. So the area under this curve, whatever it comes out as, we just about have it. But looking at the problem, let's put down a really crude estimate just to see how close we get. So the height of this is at height 1. The width of the interval is 3. So I take the area of 3, there's a lot of additional area that I have here. If I divide it by 2, that's going to be more crude than I want. Let's do it anyways. We need to be in the ballpark of about 1.5 when we go to write this out. Next thing you have to do is actually put this in your calculator and crank it out, and it's kind of awful, to be completely honest. Here's a workaround if you'd like. If you want to do this as fast as possible, it would look like this. You'd want to use something more powerful than a standard calculator, so this doesn't work well in an exam. But on an exam, I would give full credit to this. I'm not even worried about you putting into the calculator. I'm more worried of you knowing the left endpoint rule, right endpoint rule, or midpoint rule. So this is for full credit on a real exam. But for homework, we need to get the number. So let's go f of x equals 1 over 1 plus x squared. And then just hit enter on that. If you store the function like this inside Desmos, you can come down here and calculate like this. Go 0.75 for the delta x times, and instead of typing this into your calculator, type f of negative 1.625. It's just going to use the right function, and so that's a fast way to calculate these values. F at negative 0.875 plus, let me widen this out so you can see the whole thing. F at negative 0.125 plus f at 0.625. And this is the answer I was expecting. Notice it's actually about in the right ballpark when we did area of 3 divided by 2. We exceeded that, but that makes sense. We were rounding really crudely when we tried that trick out. So to 4 decimal places, we've got a 1.9086. And that's about as fast as you can do it, sidestepping the tedium. If you're using an ordinary calculator, you'd have to type in all this directly. It will work, but I encourage you, maybe give Desmos a try if you feel like you're misclicking on something and not getting the values you expect. Well, we did it, folks. That's the end of this portion of the notes. Any questions or comments at the moment?
How would you go about putting that into one of our long calculators?
It's going to look kind of rough, but let's give it a try. I think that's a good one to end on the class for. Let me go grab a, whatever this turns into, a TI-83. So if we're using like a TI-30 X2S, it's going to look about like this. Wonder what I was calculating back in the day. And this is how it's going to go in. Now, this is a challenging concentration sometimes. We've got to get it in perfectly. 0.75 at a parenthesis. Now go 1 divide. You need a new parenthesis to convey the whole denominator. 1 plus. I would take a shortcut in the calculator. If I'm squaring that, I just need the positive quantity. That's going to save you a lot of typing. 1.625, hit the power 2 key, close the denominator parenthesis. Now I've got 2 open, 1 closed. We're on the right track. Then down the line. So 1 divided by parenthesis 1 plus 0.875 squared. Close that parenthesis and continue. Same thing, but that quantity. 1 divided by parenthesis 1 plus, now we're to this portion, 0.125 squared. Close that parenthesis. If I mess up one of these parentheses, let me know. Just say, hey, Mike, you forgot one. I'll be very happy if you do so. It's super easy to do. Then one more time. 1 divided by 1. Oh, that's a mistake. 1 divided by parenthesis. Got to follow those order of operations. 1 plus 0.625 power 2. Close the parenthesis. And this is the moment of truth. We got it. That I was not sure if it was going to be a syntax error or not. Let me put this on the actual notes just to say this is what it's going to look like. It's not about that TI-83. You can do that in just about any calculator. I wouldn't attempt it in this calculator, though. This is a nightmare for that kind of work. So either way of computing, Desmos is pretty fast. A TI-83, TI-32X2S, those are pretty fast options as well. Other questions with this one, folks? Okay, I do not consider us to be completely done with these notes. There's a little bit more content, but this is all the kind of stuff you're going to see in actual WebAssign. What I have going on that we'll take a look at when we come back next week is this definition for sigma notation. This is something that just comes up more and more and more the more mathematics you take. You probably saw it in statistics first potentially, but the reason we need sigma notation out of nowhere is that is really tedious to write out. And usually if you want a good approximation, you're going for like 40 terms, something like that. You would never want to write out that many terms, so we need a mathematical way to express repeated addition. Repeated addition is in this format. If you're adding up A1, A2, all the way to AN, our notation is just to say sigma, sum up all of your A values as you start from A1, so the index is 1, as you end at AN. So that's a really compact way to look at it. We'll practice with a couple problems, but the purpose of that is, here are the formulas for the exact area under the curve. No approximation whatsoever. And notice that what makes us showing is, if you want the area to this curve, you can use the left endpoint rule, the right endpoint rule, the midpoint rule, or some other vague rule with sample points that could be anything. The only requirement to get exact equality there, and we always put an approximation symbol specifically. If you want exact equality, you're taking the limit as the number of approximating rectangles get larger and larger and larger, heading off to infinity. And notice that means delta x, which is b minus a over n, converges to a width of 0 altogether. It's kind of an interesting fact. And when that happens, the width of those rectangles are going to a width of 0. It's almost going to look like a sawtooth pattern as it gets larger. And as n goes to infinity, it will look just like that. Just one solid curve. You wouldn't even be able to see the edges of the rectangles. Their widths are going to 0. This will always work if your function is continuous on a closed domain. So that's the kind of work we're going to take a look at to get to the next section. But we'll practice this some more before we actually make that conversion. So this will be our last problem for the day, but we'll come back to more of these next class meeting. Any questions at all, folks, then, for the last problems? Okay, well, let's call this our stopping point. Have a great weekend, folks. If you're studying over the weekend, don't hesitate to write. I'll be happy to help out. Also, over the weekend, I'll start producing more stuff down here. You'll see sample final exams and other additional things to help us review for Wednesday's class next week. But have a great night, and I'll see you all next week.